No, I know a few physicists, but
Yeah, you took it last semester.
sorry guys, I'm running a little
Yeah.
behind here.
Risk assessments. Physics for policymakers. Used to science class. There it is.
That's good. Okay. All right, guys. So. Pop quiz.
Because that comes in.
As it will count for no points except for pride. All right, so I have a graph with 10 vertices and 12 edges. Is it a tree? Nope. 10 vertices, 12 edges. Is it a tree? Huh? 10 vertices, 12 edges. What's n? I'll write it down, sorry. 10, graph. Is it tree? This is the question. I got one solid no. Nodding head no. Got two solid no's. You could say no, but you're doing this. It's my favorite. Good. I hear the no though. So why?
Yes.
Why? 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 Yes is not an answer to why. Usually, I guess. Maybe you can make it. Huh? It could be. Yeah. That's like, what do you guys think? Why is it not? Yeah. Right. There needs to be. So if you have a tree, what we saw last time, one of the properties of trees, the number of edges of a tree is one less than the number of vertices. So it would have, so it would have to be 9 edges, right? So no. There would have to be 9 edges.
It's the number of edges is always less than the number of edges.
It's always one less, exactly one less. Okay, good job. The 3 definitive no's. And whoever's online who also said, was screaming at the screen or whatever. Okay, what about the redundancy? What is redundancy of this graph? This graph with 10 vertices and 12 edges. Open notes.
Got a lot of good questions today.
I want it to be a little more interactive than just lecture. Huh? it would not be one,
Oh, I'm
but
getting
thank you for the
somewhere.
response. I appreciate it.
So it'd be 10 minus 12 minus 4.
Okay, well, the way you phrase that, you have to be a little careful, but there's a parentheses in that equation. So the way you,
So it'd be 10 minus
Was 3.
3. There we go. Very good. 12 minus quantity, 10 minus 1. And then yes, this will equal 3. This is the redundancy. So what I'm trying to get you guys to think a little bit about is actually really was illustrated. Who said, someone said, like, draw us the graph or show us the graph. Yeah, okay, good. So I want to convince you that there are some things as we learn math, sometimes you can come up with answers without that, that apply to all possible situations. And so you don't need to see the graph to say, okay, is it a tree? There's certain things you can just know based on certain numbers, like the number of vertices and edges. Whatever this graph is, its redundancy is telling us sort of how many possible paths there might be between, or maybe one way of thinking of it is sort of like flexibility. If you think of like going from one place to another, how much flexibility do you have in doing that? The more the redundancy is, the more possible, possibilities you have. Okay, guys. On the other hand, I could ask a question like, what is the diameter of this graph? And then I would need more information. I can't just get everything I need from just these numbers. Very good. So continuing on the questions, just to review, because I never trust that anything I say on a Zoom lecture is at all processed by anybody. Sorry, people at home. So what is a tree? Mathematically, guys, come on, no poetry, please. It's gonna be no circuits and what? Only paths. And okay, good, right, that's the other thing. So we need connected and no circuits. So a graph is connected without circuits. You know what they call a graph? Oops, no question there. This is, huh?
This is a dad joke.
It's not a joke. Yeah, if I say dad jokes, I'm sorry. My children tell me that they're really bad and that I am. I do listen to them. Thank you. You got one, my daughter. My daughter also kind of likes them sometimes, but they still make a lot of sighs and stuff. No, this is like a real thing. So if I have a graph that has no circuits, but maybe is disconnected, they call that not a tree. So let's say I have a graph like this. What do you call this? Huh? Close. Forest. Okay, that's true.
I meant to say I.
Called a forest. Yeah, I don't know if that's in the book, but anyway. All right, so these trees have several properties. The single path property we talked about, all bridges property, every edge is a bridge. This n-1 property tells us that we know the number of edges if we know the number of vertices, and vice versa if it's a tree. And this redundancy. We talked about all of these things. I didn't tell you something which is kind of a really beautiful result. Not too hard to show, but we won't show it. I don't think we'll show it. Maybe we will. I don't think we will. Cool result though. So you can ask, So let me ask another question, which, I'll ask it. What is the number trees? I'll say labeled trees. Labeled trees. On n vertices. That's a hard question. If one of you guesses this, you're like, you get an A and you have to leave, but you can't look at your You have to go into a more advanced. Have a guess.
Just tell me the answer and not to say.
So labeled means that the vertices are labeled like, A, B, C, whatever. So if n is 2, there's only one tree. It has to be connected, so I have to have, this has to be it. N is 3. Well, we've got 3 vertices, say A, B, and C, and we have to connect them in such a way that we make a tree. So I can that, or we could that, right? Or we could do this. And that's it. Here we get 3. So for n equaling 2, there's 1. N equaling 3, there's 3. I won't draw them all out, but for n equaling 4, there's 16. Any thoughts? You might be able to, from that, you might be able to see a pattern. It's a little hard. If I write n equaling, do you want n equaling 5? I'm going to give it to you. Or not. Now you can see a pattern, right? Okay, you're seeing something. So, right. So there's a pattern of a power, right? So if you think of a power, what we have here, this was 4 squared. I think that was just observed. This is 3 to the first power. This is 5 to the third power. This is also 2 to the 0th power. So in fact, the answer is n to the n minus 2. That's a very cool result. And there's actually a bunch of generalizations of it that are much more cool. Having to do with sand pile. Sand piles. I forgive you all for not knowing anything about sand piles. But there is probably the most cited paper in the last 30 years, maybe 40, in physics. Your friend physicist was on sand piles. You drop sand and it makes a pile. But the thing is, there's like a chaotic thing, right? When the pile gets too big, it topples. There's like a toppling procedure. So this toppling procedure is actually found throughout nature. Dictates a lot of different natural phenomena and economic phenomena as well. They're sort of sudden, but has some structure, like earthquakes, things like that. Fractals. Anyway, there's notions of sand piles on graphs, and this is something, in fact, everything we're talking about has a lot to do with trees and so on. That's cool stuff. But I won't talk about any of that. I already did. Now, so what is the point of a tree? I mean, I don't know. We have one application that we can think of, which has to do with something called spanning trees. So this is section 6.2. And let's talk a little bit about it. So before I talk about spanning trees, I want to talk about subgraphs. So subgraph, a given graph is a graph sharing with vertices and edges are contained in the larger graph. So yeah, you probably. 7 or 6. Time flies. It was something. You're probably right. Okay. So if I have a graph, what's a picture here? I mean, we can talk about all kinds of phenomena. I have a graph like this. I can consider subgraphs as just maybe highlighting some edges. You don't have to have all of the same vertices, so I could just do something like this and say, okay, my red edge is a subgraph of the graph I just had. And of course, will contain the 2 vertices that are endpoints of the edge. Or you can do more. So it's a pretty, does everyone understand? Like I couldn't just, say, okay, now this is a subgraph, right? I can't draw new edges when they weren't there before. Or make new points. Gotta be contained in what was already there. Clear? Make sense? All right, so a spanning tree is a subgraph. So let's make a definition. Spanning tree. So spanning tree is a sub of a graph subgraph that is a tree and has all the vertices of the larger graph. That's a spanning part. Okay. So do I have a spanning tree? Is the red subgraph a spanning tree of this larger graph? No. So why is it not? Guys, quiet. Doesn't have all the vertices of the larger graph, exactly. So it's not a spanning tree. However, I can find a spanning tree pretty easily, right? I can just connect to the other vertices. Now I've got a spanning tree. There we go. Now I have a spanning tree. That's a spanning tree. Why would you want a spanning tree? Who cares, right? Well, okay, let's say a good example. There's a bunch of examples in the book. But I think one compelling example would be, let's say you're laying cable to like get some kind of Ethernet or whatever, like to all of the different cities. You need to connect all the cities, but you don't want to overconnect them because that cable costs money. And you just want to connect each city, make sure there's a path from one city to the other. Okay, so finding a spanning tree along your roads is a way that you can do that. So this is a very practical application, and it's actually one that's used, people look into. Another way is, if it's just whenever you have a network, you want everything connected, but you don't want any redundancy in the connection. You want to find a spanning tree. Okay. There are formulas for the number of spanning trees, which, as I said, that's like this n to the n minus 2. It's very interesting, but yeah. Take that for another day. So let's look at this practical application. So last time, we had this, I had this map I drew, which I'll draw again. These cities. And we put weights on them. So in practice, a tree is great, but usually you have some weights on these edges to sort of tell you the cost or the distance or give you some measurement of how that you want to minimize, like how long the distance is or how much something costs to do something. So these were miles. And if you're laying cable, for example, or, obviously the thing you want to do is minimize the number of miles that you have here. So if you want to lay cable and minimize cost, then what spanning tree do we look for? So what should be the quality of how many edges, by the way, will we have in whatever spanning tree we find? Okay. I'll repeat the question. So how many edges if I find a spanning tree, how many edges will there be in that spanning tree for this particular graph? I didn't know what that, are you raising your hand or are you telling me the answer? 3, right? Because there are 4 vertices and the number of edges of any tree with 4 vertices is 4 minus 1, which is 3. How many possibilities are there? How many possible spanning trees are there? Noting that this is a complete graph. So any labeled graph with 4 vertices is going to be a spanning tree. So there should be 4 to the 4 minus 2. 16. So there are 16 possible spanning trees here. I don't want to draw them all. Can you see, just by looking at this, that the spanning tree that will minimize my cost if I'm laying cable? This example makes us seem pretty important. At least our location. Right? Okay. All roads lead to Rome. Manhattan, I mean. I don't think that's the thing. Maybe in New York, it is, but not really.
How do you say that? That's what I was thinking, but I have no idea how to like verbalize that.
I would say take all edges incident to M.
Okay.
Take all edges with M. as a verb. That'll be easier. Or use your own words. Use your own words.
I don't know, like, sometimes you have to say in like a certain order or something,
I agree. Words are words.
like the quantity of.
Yeah, I
I know
get
in
it.
that situation.
It's okay. It's okay. Yeah. So here what we can see is why are we convinced that this is definitely the best we can do? We know we need 3 edges, right? Because we know trees have with 4 vertices have 3 edges. So why is this the best tree? For sure. Because it's the lowest number. If we look at the edges here, these 3 edges have the smallest numbers out of all 6 edges, right? So we're not going to be able to do better than this. If we took any other edge, we'd have a bigger number. So this is actually one of these cases where it's actually should be pretty easy. And now what we found here, what we're looking for is what's called a minimal spanning tree. And that's equal to a spanning tree with the smallest total weight. Now, I want to ask you guys another question. Just in that kind of mood. Let's say you were not laying cable. Let's say you're in a company that sells cable. And you have a proposal to these 4 cities of how they should lay their cable. So what are you? Yeah, good. So the goal there, you're not going to get away with telling them, listen, guys, you should lay a cable between all of your cities. Like they're smart. Us here in Kansas and Lincoln, Nebraska, we're smart enough to see right through that. You might get away with saying, hey, we've got a spanning tree here. So we're just connecting every city to not another city once. And here it is. We're going to give you a spanning tree that has the maximal total weight. You won't say that part. So seller of cable propose maximal spanning tree. However, you can see that you can't do exactly the same thing that we did before. So if I took the 3 largest edges, right, of this graph and made a subgraph of them, what would I get?
TWLN.
It would be T, if I just took the 3. So I would get T, you're right, TWL, but I go back to T, right? So I would get a circuit. I would not get a spanning tree if I took the 3. So in fact, the largest spanning tree here, or the maximal spanning tree, is actually this tree. And we'll see the algorithm now on how to find this. So this algorithm is used, it's a very simple algorithm. It's an optimal algorithm, not approximate algorithm. And yeah, it's like really easy. And it's familiar to what we were doing with finding Hamilton circuits. Questions, anyone? Algorithm. For finding max, we'll say minimal. There's the same algorithm can use to find maximal. We'll talk about the minimal case. You have to adjust it a little bit. It's called Kruskal's. I don't know anything about Kruskal. Seems like a nice guy giving us such a sweet algorithm. It's familiar, so it's very similar to this cheapest link algorithm that we talked about before for finding Hamilton circuits. Of course, this algorithm is optimal, so it works. It gives us the best solution, and it's fast, and it works on any graph. It's not just a complete graph. So step one of the algorithm is pick the cheapest edge. Like if you want or whatever. Step two, pick next cheapest edge. Not all algorithms are this simple. I mean, like, I know this can be tedious for everybody, but this is, guess what you do for step two? You continue. And the only rule, so before there was, when we did this cheapest link algorithm, we had a requirement. When we were finding, we always had to make sure that we didn't form a circuit and that we didn't make a vertex with degree 3. That was the cheapest link algorithm. However, now we actually have less that we have to avoid. We can make degree 3 vertices or degree anything vertices, but we can't make a circuit. That's the only rule. Continue without making circuits. In other words, picking the next cheapest edge without making a circuit. And then step n-1, finish up. Says, let's say graph has n vertices. Finish up, I mean, pick your last edge. Okay. Let's do this out. Let's perform this algorithm on a graph and make some observations. So I haven't weighted this. Let me weight this graph. So each edge I have to give a number. And just like in the case that we had when we're finding Hamilton circuits and paths, here we may have some redundancy. So it may be the case that there are some edges that have the same weight and you have to make a choice. That's okay. So let's say I give these two edges the same weight and give both this edge and this edge the same weight. Okay. So let's perform Kruskal's algorithm on this graph on the right here. Of course, this will only work. We can only get spanning trees if the original graph is connected. So we have to assume connected, that we're starting with a connected. Okay. So what do you think? What do you think I should do here for my first step? What should I choose out of all these edges? The 10, the edge with weight 10, right? So in fact, I have two possibilities here, but as you can see, once I choose one of them, the next cheapest link is going to be the other. And it's not going to form a circuit, so I'm going to have to choose the other in this case. However, now, what's my next cheapest link? 11. And I have two possibilities. And depending on which one I choose, I'm not going to choose the other. So you can, you know, we've got, at least for now, we've got freedom of choice. Let's see. Let's choose there. Good. And as I said, we can't choose the other 11. Even though that's the cheapest link, we can't choose it because we make a circuit. So we skip it and we move on to the next cheapest link, which is clearly 12. And then we have, I believe, 14 and 17 are the next two. And we don't have to, each time, these choices, clearly they're not giving us circuits. So we're feeling good about ourselves. And now we just performed, let's see, 1, 2, 3, 4, 5, 6 steps. And if I count the vertices, I've got 1, 2, 3, 4, 5, 6, 7 vertices. So I'm done. Or you can look at it and see I've hit every vertex with this graph, with this tree. And amazingly, this is a minimal spanning tree. This has the smallest total weight out of all possible trees. There's a lot of possible subgroups from spanning trees. So the fact that you get it this quickly, is this easily, is pretty impressive. So if you were ever in charge of a company that lays cables or that needs to set up certain networks, hey, you guys, you know, it's a brave new world, you might be. You'll know exactly how to find the most efficient way of doing so. Most cost effective. And you'll know the best way to also charge the most amount of money. So, I mean, another option, if you don't like to be like, you know, capitalistic or whatever, and you want to, well, or at least like deceptive, let's say. And you want to like, I don't know, like let's say you want to maximize something like you like running and you want to maximize the number of miles you run, but you want to visit each city once. I don't know. It's kind of, you know, then I think you need a circuit, but okay. Say you want to set up a taxi service and you want to maximize miles. That's sort of capitalistic, but okay. You can still do Kruskal's algorithm is what I'm saying. If you want to find a maximal spanning tree, you can do Kruskal's algorithm, but now you just have to replace cheapest with the most expensive, right? So if you want to kind of reverse this algorithm, you just make it the most expensive. And if you do that, we can try that algorithm. So maximal spanning tree, we'll look for the longest or most expensive edge. I think 35 looks like that's the one, right? So let's do that. Blue. Then 32 looks next, right? Tell me if I'm making a mistake. What's next? 28 or 30? I think, yeah, 30. Okay. Now I think 28 is 28's turn, right? Okay, now I'm almost done, right? So, but now I have to be a little more, you know, a little more judicious about what my algorithm is telling me. I think 20 is the next most expensive one. But if I chose 20, I would get a circuit, right? So similarly, 17 would also be the next in line, but if I chose 17, I would get another circuit, like without forgetting about that edge. If I chose 17, I would have this circuit here. Similarly, 14, which is next in line, would give me a circuit. So I can't choose any of those. So what do I have to choose now? Not quite. If I choose 11, I'm gonna have. So I'm not quite almost done. I know I need 6 and I've only got 4, so I'm gonna have to make 2 more steps. If I went with you and I chose 11, like say I chose that, then I would have prohibited choosing 12. So I can do, right, so the next, I think if I rule out, if I go down the line and I say, okay, I can't choose 20, I can't choose 17, I can't choose 14, the next in line is 12. And so I'm gonna choose 12. And now, what can I choose? Now I can choose an 11, but I have to choose the right 11. Maybe this one. I get and this will give me a maximal span. This one gives me a min. How do people feel?
This is very tedious.
It's tedious?
Yes.
Well, welcome to my world, man. It's the way it is.
So when you look at them yourself, do you like automatically see the pattern or whatnot? If you're just
No, I cannot automatically see it better. Absolutely not. I cannot see it better. Because these circuits prohibit the pattern, right? In other words, I have no idea that if I just look at this original graph and I think, hey, is there I have no idea whether 17, I would think, if I looked at it, I would think 20, that's probably going to be in a spanning graph, a maximal spanning graph, but I'd be wrong, right? So it's not one of those things that it's like it's not like the first example I gave, right? You can look at it, I think, and say, just choose the smallest ones. Here, if I choose the top 6, what do I get? I'll get 30, 32, 35, 28, 20 will be among them, 17, right? Those would be the longest or most expensive edges. And so I don't see at all when I look at it, which ones are going to be there and which ones aren't. The most expensive one. So I don't know. You just have to perform the algorithm. It is tedious. It is tedious. I mean, of course, computers do this. We program computers to do this. I always said to my students, like if I'm an employer, and I have been on many hiring committees, and I'm hiring someone, I don't want to hire someone that is a computer. If I hire a computer, why don't I just buy a computer? I want to hire someone who knows how the computer works and knows how things, knows how to solve problems with it. Right? Who could program the computer, who could actually. So learning stuff like this is, I don't want you to become the computers and do this 1,000 times. I want you to understand how this works and then move on, right? And then we'll go on to the next kind of problems that we can solve. All right, so moving on. So I don't think I'm going to be able to do what I wanted to do. So I don't think I have enough time. But so I do want to get just a little bit started on the next chapter, which I guess is What, 18? Wait, no, 8. Sorry. I really don't. I look at the book. I want to kind of follow the book, but I try not to like do any of their examples or anything. So I just look for the basics. I'm gonna be honest with you guys. I don't know anything about scheduling as like a theory. This is not my subject at all. The other stuff, I mean, the graph theory, I know a substantial amount about, more than I should. But scheduling theory, I don't know. So I'm kind of learning the words for scheduling theory. When we get to directed graphs, I'll be able to shed light on things. But there's some vocabulary, I guess, with this theory. And okay, so there were 4 sort of main. I'll go over some of this in more detail on Monday. There are 4 main things that their scheduling theory have. They have processors. Those processors complete tasks. Each task has a certain processing time. And then the most important thing, which kind of makes a graph out of all of this, from my current understanding of things, is that there are precedence relations. So what does that mean? That means if I have several tasks, some tasks you have to do before you can do other tasks. That's the gist of it. So I wanted to give an example. I don't know. We'll see if I have enough time. Let me try it. An example puts tasks at the sort of center of things. And I felt like this would be a good lesson for all of you. I don't know. We'll see. So these are my labels for my tasks. There's too many of them. But well, you will have to do, this is the whole point of this exercise. Okay, guys. So CC is cooked chicken. EC is diced chicken. PN is prep noodles. P is just prep. So prep means, of course, you want to dice garlic, carrots, onions, and celery. All the A's are adding things. So add butter, garlic. I was a sous chef back when I was your age. Gotta make sure you guys know how to do this. I added butter twice. Ah, broth. That's BPR.
Michelin star.
That was a pretty good restaurant, Garytown Bistro. That's where I met my wife. Server. I was a sous chef. Rest is history, kind of. So listen, precedence relations. Do you add the celery before you cook the chicken? There's one thing there's also 2 other tasks, which is taste and season. All right, I'm going to give you guys a real lesson in precedence relations on Monday. You can study for this, though. You can study for this. Very important, the order of operations.
versus what should be in early next week. So.
Have a great weekend. Thank you.
Yeah, you too.